topics. The first thing I wanted to say, though, was just to remind you that it's a very collaborative effort, Phenix. And what I'm going to talk about today is actually not mainly the work of my group, but it's more the work of Randy Reed's group, of course, who developed Phaser. But also some of this that I'll talk about was done by Tom and in a collaboration with the Rosetta folks, David Baker's team. And just to remind everybody, molecular replacement is the other way to solve the phase problem. And as we said this morning, it's actually the predominant thing that we tend to do these days in crystallography. But clearly, if you're trying to solve a new structure, you've got to go down the routes that Tom mentioned. And I'm going to assume that people are sort of familiar with the idea of molecular replacement, so I'm not going to talk a lot about the background to the technique itself. But just to quickly remind folks of the idea that what we're trying to do is we've got a crystal with molecules in it, and we've got a molecule, a model that we believe is similar to what's in the crystal, and we're going to try and place this search molecule in the crystal. That's the goal of molecular replacement. And the way we typically do that is to divide it into two problems. So it's a divide and conquer approach, where we make it a simpler problem by trying to solve the rotation first. How does this known structure, how can we rotate that to best match the crystal? Once we've done that, we might be able to optimize a bit after we've done that, but the second part of the problem is then how do we translate that molecule to see where it goes in the crystal? And we're really trying to say what's the translational relationship between the molecules based on symmetry. So that's the second part of the problem. And that makes this a tractable problem, because if we had to do a full 6-dimensional search, it would take a lot of time computationally. It's not impossible to do, but it would take a lot longer than trying to do 2 3-dimensional searches. So this is the general approach. We're going to collect some data. Only have to collect amplitudes, right? We don't have to do lots of anomalous experiments, so that's a good thing. We might look for symmetries of certain kinds, and that will come up later on in the talk. We're going to make a search model, and I told you this morning that's a really important, crucial part of what we do. We have to make a good search model for this to work. For each model we're trying to do the rotation first, then find the translation. We're probably trying to optimize the result of that by rigid body refinement, and if we have to find more molecules, we'll go around and keep doing that. And at the end of the day, we'll have a set of atoms placed in the crystal that we can calculate phases from, and that gives us maps, given our observed amplitudes. So we've solved the phase problem. Some of the great things about this is, one of the great things about molecular replacement is we only have to use the observed amplitudes, not differences between amplitudes, which means, not that you should do this, but they don't have to be that accurate. Not to say you shouldn't do a good experiment, but molecular replacement will work even if your amplitudes are not as accurate as you'll need for experimental phasing. In terms of solving the problem, though, it actually shares a lot of the things that go into substructure determination that Tom mentioned in terms of Patterson methods, because that's the kind of information we can use when we don't have anything apart from a set of amplitudes. As I said this morning, it's about 70% of structures that are in the PDB annually now come from molecular replacement. And the good news for practicing crystallographers is this can be quite automatic in a lot of cases now. So that's good news.
So again, what kind of resolution are you using here?
All sorts of resolutions. People solve problems at, we've done things in my group at 6 angstrom resolution. But people are often doing things at 1.5, 2, 3. That's the other good thing about replacement. You don't have to have high resolution for it to work. So one thing to realize is that what we're really doing is trying to test various positions or various rotations or translations depending on where we are in the process. And the way we're going to test those positions for the search models is by scoring of some kind. And this relates a bit to what Tom was saying as well, that we can think of this as a search problem, or in the likelihood case, we'll get to that in a second, with a whole different set of potential solutions, which are the ones that best predict the data. Historically, we use maybe things like Patterson product functions. Take two Patterson maps, multiply them together. If they match very well, you get a high score. If they don't match, you get a low score. You can do the same kind of thing in reciprocal space. You can calculate correlation coefficients between reflections in reciprocal space. But this is just a way to score a location of a set of atoms compared to some observed data. So these are the things that, historically were kind of used for rotation functions. Same concept when you do the translation function. A lot more options there, but you can imagine things like correlation between amplitudes, intensities, things like that as a way to score, is this a good place for this molecule or not? Now, it turns out that if you do the scoring on the basis of squared amplitudes, so intensities, you can actually calculate this correlation coefficient very quickly with a fast Fourier transform. So that's typically what molecular replacement programs have used, is some form of an intensity-based correlation function, because we can do that very quickly. So the reason to tell you that is to say a little bit more about likelihood, really. And Tom brought up likelihood, so I won't say much about it, but same idea that really the good thing about likelihood is we're talking about what's the best model, or the best model is the one that is most consistent with the data, the one that predicts the data, which is sort of the opposite way around from the way we think about things sometimes. And again, the consistency is measured by probability in terms of likelihood. So I won't dwell on these things so much, except to say more about, well, what's the advantages of this? Well, in molecular replacement, we can try and estimate errors or differences between our search model and what's in the crystal. We can incorporate that in the likelihood function. Traditional molecular replacement kind of assumed that what you're searching for is exactly the same as what's in the crystal, which is clearly not right. We hope it's not right. We can take an account of lack of completeness of the model, for example, which again was not really treated for in traditional molecular replacement. As I said this morning, we can take information from a partial, so like we find the first molecule, we can actually incorporate that into the likelihood function to help us find the second molecule. In the old days, we had to just try and find them one by one and hope we could stitch it all together. And as I said this morning as well, we can take advantage of ensembles. We can take advantage of the fact that there are commonalities between models in an ensemble, but there are things that are different. We can take advantage of that in molecular replacement. And the formal way to do that correctly is through likelihood. So that's why likelihood has enabled a lot of these things here, that you can't really do this really can't do this at all with traditional molecular replacement approaches. But, so having said all of that, those are great things, but in practice, what does that really mean? What it really means that when we use likelihood in molecular replacement, we're changing these scoring functions. That's essentially the difference. And so I'm not going to go through these here. These are what was derived by Randy and colleagues, but you can see they're different from what I showed you before, but they are still scores. They're something that takes into account the structure factors that we observed, and then structure factors that we can calculate from the model, experimental uncertainties, and then uncertainties we can estimate from the model as well. So that's the fundamental idea. And it turns out that the translation function score here is the same as the likelihood functions we use in structure refinement. So if you use refinement, Phenix refine for refinement, or you use RefMac, this is essentially the form that Rho's target functions take. It's this kind of likelihood function. Now, having said that, these are sort of the exact likelihood functions that one would want to use. It turns out these are slow to calculate. So in practice, during the molecular replacement, say in phasor, slightly modified forms of these scores are used to make it quick, so they can be estimated by fast Fourier transforms, for example. But at some point in the process, which we didn't talk about this morning, these full forms of the likelihood function are used to rescore things. So one thing to realize about these equations here is some of these variance terms here, this sigma s, for example, they're saying something about how well we believe our search model matches what's in the crystal. And that's an important thing because it allows us to account for the fact that there's a difference. But it also means that the program needs to know something about those variances before it knows where the molecules are and before it knows the answer about what's in your crystal. So that seems a bit contradictory in a sense, right? We have to estimate something before we know the answer. So that means that we have to have some way in this process, doing molecular placement with likelihood, to describe how similar or how different our search model is compared to what's in the structure, in the true structure. And I'll just talk a very little bit about how that's done in a minute. So, but just say a little bit more about the practicality of likelihood so you can think about it in a slightly different way. And this comes down to uncertainty in the positions of atoms. That's what we're saying about a search model not being exactly the same as what's in the crystal. It means there's some uncertainty about where those atoms really are. That's one way to look at it. And if you think about what's happening in real space, if you have uncertainty in the position of an atom, it could be something like this. The atom is here most of the time, but maybe it's left or right, shifted left or right. Yeah? And let's say it's a Gaussian distribution because that always makes life a lot easier. So in real space, we'd have this. If we did a Fourier transform all of this, and we looked at the scattering from each of these positions of the atoms, left or right, we will get something like this in the complex plane in reciprocal space. Yeah, the centroid position here would lead to a vector pointing here in the middle, but we would get structure factors that would point, for this one particular atom, yeah, nothing else, that would point in different phase directions. The amplitude would still be the same because there's the same number of electrons scattering, but where that scattering vector goes will be slightly different. And we'd have this boomerang type distribution here. And what's the center of mass of a boomerang? Anybody know where the center of mass is for a boomerang? Yeah. So center of mass for a boomerang would actually, like the distribution like this would actually sit, say, somewhere over here. So if we took the average of this distribution, it would be the shorter vector that we've shown here.
Like the center of mass of high jumpers goes under the bar.
Yeah, yeah, right.
Factor sum too, all this
Yeah, yeah, exactly. So when we have uncertainty in the positions of the atoms, the structure factor that we predict is actually really shorter. Yeah. Now, that was one atom. What happens if you have a lot of atoms with Gaussian errors on them? Well, those all add up, central limit theorem. So if we looked at overall structure factors from all sorts of scattering events throughout the crystal, we would get this kind of picture where we have what we would calculate, assuming the atoms are all perfect, this vector here. But because of uncertainty in the positions, we would actually say that, well, this it's got to be multiplied by some factor d here to shift the distribution here. And if we have uncertainty in the phases, then of course we have uncertainty in the direction of this structure factor as well. It's another Gaussian distribution. And this is important for the likelihood function because that's what it accounts for, this factor d, effectively. We can quantify this with a parameter. It doesn't really matter what it's called, sigma a in this case, but this is a combination of model error and completeness, the two things together. And in practice, we can estimate sigma a by comparing our observed and calculated structure factors. There's a correlation coefficient between the two. Of course, we don't know FC at the start of molecular placement, though. So again, we have this problem. Yeah? We don't know where the model is. And this just shows you down here that if you make different assumptions about how good or bad the model is in terms of sigma a, it leads to very different probabilities of given structure factor given the observed structure factor. So it's important. So what do we do? So in practice, sorry.
So that also depends on the resolution. That is, at low resolution, that boomerang must almost always be smaller.
Yeah. So I didn't So I didn't show you that on that slide, but it kind of is shown here. This is this distribution of sigma a with resolution. So you can see at low resolution, you have, as you say, essentially more narrow, more confidence, effectively. So what we do in practice is to say, well, we actually know something about RMS deviation of models given sequence identity. this was work that goes back to Chathier and Lesk in the mid-80s. I remember reading this as an undergraduate, this paper. And what they did back then was just plotted, given the small number of structures available, sequence identity of the models against their deviation in terms of coordinates. And they found this distribution here, which actually still holds. You know, you can do this with thousands and thousands of structures now, but it's still the same thing. So what you can do is, if we have a sequence identity, we can use a graph like this to read off what that relates to in terms of RMS deviation. And then, because sigma A is related to RMSD, we can convert the RMSD into a sigma A curve and use that sigma A in the likelihood function. So this is why it's very important that you have some idea of sequence similarity or some estimates for how good your model might be compared to what's in the crystal. Now there are complications, and there are sort of ways that this can be done better, and Randy's group is looking at ways to improve this, but fundamentally it's the idea. So as I said this morning, and I won't dwell on this, but just to say that automation is a very important aspect in Phaser. It does a lot of bookkeeping for you that you wouldn't do for yourself. That makes a lot of problems solvable that weren't solvable before. This just shows you a flow chart we won't go through, but a flow chart for what's being done just trying to solve a two-body molecular placement problem in terms of searching over space groups, etc. And you can imagine trying to do this yourself by hand would be tedious, if nothing else. The chances of making a mistake are pretty high.
Excuse me. So what do you need is likelihood function for just to fit into the figure measure of phases, or what?
The likelihood function, we're going to use that to score the rotation or translation of a molecule. When we put a molecule in the asymmetric unit, we can calculate the likelihood function, and if the likelihood is high, that means this is a good place. It's predicting the data well.
Yeah.
If it's low, it's not predicting the data well. It's a bad place to put the molecule. So it's just a scoring function. It's not, in this case, it's not to do with phasing per se, but it's to score positions of molecules as we put them in the crystal.
Okay, so that would have been greater if you have many solutions, right? But if you have only one solution, you have no choice.
But it's a search problem, though. We have to search over many possible orientations. We're trying to find that one orientation where it looks good.
So you use the scoring function for that.
For that, yes, exactly. And it is good because it's discriminating generally.
Okay.
Yeah. So, just to say a little bit about the search model, because we talked about this briefly this morning. There's a lot of things you have to think about here when you make a search model. How are you going to align sequences? Do you just take your protein, align it against one sequence and say that's my alignment and that's what I'll use to generate the best model? Maybe you could do a multiple sequence alignment. That often gives you more discrimination. You've got potentially domains that you could be looking for. How do you identify those domains? Yeah, that's sometimes a non-trivial problem. What sequence do you actually put in your model? Do you just keep the sequence of the search model, which you know is incorrect? Do you mutate it to things that are close to what your true sequence? Some people like to do things with C alphas only, or just the polyalanine backbone search models. There are arguments for and against this. Sometimes you might believe that your molecule has undergone some change. So maybe you have to think about generating a set of models that might sample possible changes in terms of structure. So some people have worked on exploiting normal modes to do this. And then you can imagine you could come up with lots of different models here, potentially. So, sorry?
So your error model would assume that, okay, I have all the atoms in, I have accounted for all the atoms that I expect to be in.
No. That likelihood function can account for the fact that we don't have all of the atoms there.
Okay.
So we can search for a small part or a small fraction of the atoms. That's part of that error model, effectively. Yeah. So there's a second question here, which is, how do you make use of all these models? Do you just take one that you think is the best? Do you take many and make an ensemble? Do you try the many one by one? these are things that are not necessarily automated for you all of the time. So these are things that you should think hard about when you make your model, because this is a point at which things can fail, especially if you have borderline sequence identity. So there's a tool in Phenix called, two tools, Sculptor and Ensembler, that help in this process. So Sculptor is a tool that will use a sequence alignment to change your search model to give you the best set of atoms, potentially by trimming away loops that aren't in your target, by changing the residues to look as most like your residues, taking the core conserved parts, adjusting B factors, for example. So these are all things that will be done by Sculptor. Then Ensembler is a tool that will help superimpose a set of models to give you an ensemble that you can then use in molecular replacement. And again, for difficult problems, this can be a very powerful thing to do. So just to show you one example here from Randy's group that of taking, this is a serpin, taking many different serpin structures here and overlaying them. So those are overlaid automatically with Ensembler, which does an iterative weighting of the secondary structure elements to try and give you a well-aligned core of the structure. So that's what you can see here. But then it can also be used to trim off all this extra stuff on the outside. Because if you did molecular replacement, it turned out with this, even though this represents both the conserved core but also variability, it didn't work. Whereas if you pare it down to this green conserved core, the molecular replacement did work. So you can see that might make a difference. And this just shows you that you can use Sculptor and Ensembler together to make multiple different kinds of models. So not just taking one best model, but doing slightly different procedures. And this just shows by a set of models ranked by, this is sequence identity at the bottom. So these up on the right are easy to solve. Things on the left are very difficult. And this is the number of models that were available. Using the default approach in other programs, Chainsaw is an example here, to generate models. We can solve all of the purple ones with Phaser. If you try different approaches to making the models, changing the B factors differently, using polyalanine versus full sequence, you can then actually solve these additional blue ones. So as you can see, it makes little difference when you have easy things to solve. It makes little difference when things are really hard, because they're just really hard. But the things in the middle here, you can substantially improve the number of models you can use to actually solve these molecular replacement problems. So that just highlights the fact that the difference between solving or not solving could rely critically on having a slightly different model. Okay, so how do you know if molecular replacement has worked? I mean, this is a common problem. You do it, it's either very clear that it's worked or you don't know. So Rob Oefner in Randy's group in Cambridge did a whole set of thousands of molecular replacement problems here, and then did a statistical analysis. And this just shows you on the left here so this is the things divided out into failures in red and successes in blue. And what you can see, of course, is that once you get, this is scored by translation function z-score, so how significant the translation function result is compared to just random solutions against frequency. And you can see that once you get very high translation function z-scores, these things are all solved. And if we zoom in on the graph here, what you can see is that once you get above 7 or 8 in terms of translation function z-score, you're pretty much likely to be correct, to have got a solution. Conversely, of course, if you're down at 3, 4, 5, chances are that it's incorrect and not solved. Tricky thing is there's a region here between, say, 4 and 6 where there is a finite probability that you will have solved the structure. And I'll talk a little bit later in the talk about those cases which can be very difficult to get any further with, and ways that have been developed to try and get past that. But hopefully this is sort of useful guidance for how to think about whether you've got a solution or not. Now, there's a caveat here, which is these are single molecule molecular replacements where there's just one protein to be found. It no doubt is slightly more complex, or the graph looks somewhat different when you have multiple components. and Rob is working on that, but you know, as a baseline, this is a good guide. Okay, so the rest of the talk I want to talk about a handful of things. Hopefully it won't take too long. And that's really around limitations from electroplacement. And the first one is, I mentioned likelihood. Likelihood makes assumptions, or is built upon certain assumptions in terms of the distribution of intensities in our diffraction data. And there are cases where those intensities are unusual. And I'll highlight one of those. And traditionally those have been problematic. And I'll talk about what's been done to try and solve that. So that's one issue that I'll talk about. Then another issue is, well, what if I want to do molecular replacement but there's no search model? What are my options?
How can that be? You can always search for some protein with some sequence identity, right?
Well, not if it's 5% sequence identity. You can do the search, but the chances are that you're actually searching for something that is not related to what's...
So you need the sequence identity to be above 20% or?
Well, there's no definitive answer to that, but all you can say is as the sequence identity gets lower and lower, the probability that you have the right structure to search with is lower and lower as well. That's just the way it is. So there's a lot of times where you will feel quite confidently that you don't have anything to search with, really, yeah, realistically. And I'm not going to present a miracle here, but unfortunately.
Is there any way, either in existence or in development, to do a localized sequence, sort of take something from something else that you know the whole thing doesn't apply, but maybe a particular smaller portion may?
Well, so I think what I'm going to show you in terms of Rosetta very briefly is sort of gets to that. The idea that I could... sorry? Yeah, no, you can run fire, you can run all sorts of things to try and get models. So in a sense, Rosetta sort of tries to do that in one way. And I'll just mention briefly some work some other people have done that, you know, where you can exploit the idea of smaller secondary structure elements or motifs, which is kind of what you're getting to. But the idea of being able to take 5 residue fragments and do molecular replacement piece by piece is still not there yet. I mean, maybe one day it will be, but it's not there yet. So that's one issue. We won't spend much time on that, to be honest. The other thing that I will talk about a bit more, and this is work from Tom and Randy and the Rosetta people, is this case, and I just showed you the cases where you think you maybe have a solution, you're not really sure, you can't get anywhere with it. What can we do to try and get past that bottleneck? Because that does happen, and maybe more than people realize. So the first issue is this, you know, unusual intensity distributions. So, and the topic here is translational non-crystallographic symmetry. Has anybody encountered that in their crystals, translational non-crystallographic symmetry? Maybe, maybe not. Some of you have for sure. If you do enough structures, you will. I think that's probably the bottom line. So non-crystallographic symmetry is quite common in crystallography, macromolecular crystallography. About, you know, a third to half of structures actually have some kind of non-crystallographic symmetry, and some subset of those it is actually in the form of translational non-crystallographic symmetry. And this comes around because you can have rotational symmetry that is parallel to a crystallographic axis. And historically, this was a class of problem where likelihood methods for molecular replacement, i.e. phasor, failed. It would find maybe 3 or 4 of your molecules, but wouldn't find the other 1 or 2. You get very strange results. It'd put molecules on top of themselves. It would be very strange. And that's because the intensities, when we have translational non-CS, are not what we normally expect. So just to be clear about what we're talking about, imagine this example here where we have a dimer here, a pink molecule and a blue molecule, so they're maybe the same or very similar to each other, related by a twofold axis. There is a twofold crystallographic axis. When you apply symmetry, you end up with a molecule over here. So the pink and the blue molecule here are related by a translation. Yeah? So that's not uncommon to actually encounter. So what happens to your crystallographic data if you have something like this? Anybody hazard to guess when you have something that looks like a translation in real space, what happens in reciprocal space? The older people can't, I shouldn't say older, the more experienced people shouldn't answer. So any of the students come across this before? So what happens when you have centering in your crystallographic symmetry? Do you see all of the reflections that you would see if it weren't centered?
The old farts have a hard time getting the young people to look at reciprocal space.
Okay, so there is this thing called reciprocal space. So just to tell you what happens, when you have you have a molecule in your crystal and it's translated by essentially half a unit cell, let's say, and you got another one in exactly the same orientation. I don't have two left hands or two right hands, so I can't do it properly. What happens is you get, in the diffraction space, you get cancellation of the diffracted waves. And it means that systematically there are reflections that will be missing in reciprocal space. That's what happens.
It looks like your unit cell is half as big, so the spots are twice as far away.
Yeah, you can think of it that way, but you've got reflections that disappear in reciprocal space because of a cancellation effect in terms of the scattering. So this is why it's good to think about reciprocal space some of the time, because it's relevant to what we're actually doing in crystallography.
So that will cause a problem in the identification of the space group, right?
We can do, not typically. It can do if that translation is not quite crystallographic, because when it's not quite crystallographic, what you can imagine what might happen is the reflections are nearly cancelled out, but not quite. So you get some very weak reflections. And this is what happens when we have translational non-crystallographic symmetry. It's the same effect that we see, depending on the orientation of the vector. But essentially, we will end up with a lot of reflections that are very weak and a lot of reflections that are very strong. And that makes your data look not like typical crystallographic data. It's just the distribution of intensities is not the same. And you can think of things being like this. If we had two molecules that were identical to each other and related by this, just a translation, that would be perfect translational NCS. It's not what we typically have. That often actually is crystallographic, comes down to a centering operation. What we typically have is something like this, where two molecules are not exactly the same. It's not just a translation, it's a bit of a rotation. That's more the reality of what you see in these circumstances. So the challenge is, how do we tell the likelihood functions about this systematic change in the intensities, especially before we know where the molecules are, right? The only thing that we could hope to get prior to solving the structure is the vector that connects these two molecules, because we can get that from a Patterson analysis, from a native Patterson. And if people aren't sure why you can do that, we can talk about it later on. So the solution, it turns out, is to, what we can do is we can determine the translation vector between molecules in the crystal, like I say, from the native Patterson analysis. We can approximate our molecules by spheres. They're not spheres, but to a physicist, that's a good thing for a molecule. It's fine. And then, given that we can put these spheres somewhere, we can actually then optimize a function that says, well, what's the rotation between the two spheres in reciprocal space? And also optimize the translation vector, because it might not quite be half a unit cell, it might be 0.47 in fractional space. And then we won't go into the math behind this, but you can then represent the effects on the diffraction pattern and the intensities with this, what's called an epsilon factor, which is part of standard description of reflections anyway. We just never talk about it. This is a weighting factor that takes account of some aspects of symmetry. But when we have NCS, these are typically integer values. When we have translational non-crystallographic symmetry, we can actually obtain non-integer values for these. So just technically, that's what's being done. And I won't go into this, but just to say that we can have a likelihood function here that is used to obtain the values for these epsilons by optimizing parameters of these spheres and their rotations and translations with respect to each other. So in practice, what you might see when you run Phaser and you look at the log file is that it will say it's looking at pseudo-translational NCS. It's found a big peak in the native Patterson map. It has this vector in fractional space, and it then will go and try and refine the orientation of the molecules with respect to each other, even though we don't know where they are right now, and the actual value of the translation. And you can see this translation vector refines to something that's not exactly halves and 3/4 or quarters. So that is what's being done now in Phaser, and you don't have to turn this on, this is done automatically behind the scenes. It's trying to correct the intensities for the presence of this translation. So does that make any difference? Well, I'm not going to tell you unless it did, of course, but this is an example from Gideon Davis's group in York, something they solved in two crystal forms. One they could solve, the other one they couldn't, and that had a translation component to it. And this just, we'll look at what happens if we try and solve this using different approaches to the translational NCS. So if we don't take account for the translational NCS, we get very poor discrimination in the rotation function. These are translation function z-scores. So we actually find the right thing is the top peak, but it's not very far away from an incorrect peak, and you can't solve the translation function actually with the original approach. It just doesn't work. In fact, the top peak that you get is wrong, and the right peak is not in the list. So that's a problem. If we treat this as a pure translational NCS, where we assume the vector is, some very well-defined fraction in the unit cell, we actually make things worse in rotation space, but we can improve the rotation function. Sorry, the translation function. The translation function, now we find the right peak as the top solution. If we do the more correct thing, which is to assume this is pseudo-translational NCS, where there is some rotation and the translation is not exactly some fraction of the unit cell, then we get better discrimination at the rotation peak level. These are better separated, and the only peak we get out of the translation function is the right one, and it has a much higher significance. So now you should be able to put in a case like this into molecular replacement, and it should work. So problems with translational NCS should be readily solved. And for those of you that have encountered it before, you probably appreciate that's kind of good and a big deal. What isn't done right now is to deal with a case where it's more than one translation vector. Sometimes you have unfortunate cases where you have multiple translational relationships between molecules, and that's more complicated. So onto the second problem, extending molecular replacement. So what can we do if we don't have a search model? Well, you can run fire, you can take your low sequence identity things and pray, see that it works. One approach, though, has been to use ab initio model generation. So Rosetta is one approach to that people are familiar with, I think. There are other things. There's the Zhang server, for example. So there are lots of tools out there, actually. The idea here is that, the Rosetta takes small fragments and essentially folds them up to give you a model. It'll do that for probably 120, 150 amino acids. Beyond that, it gets computationally intractable. But they've had some success in doing this, and in one of the CASP competitions, it was shown that you could take the model that they predicted and use that to solve the crystallographic data by molecular replacement. And that was a few years ago now. That's this example shown down here. The problem, as you might imagine with the approach, is to do this, you have to generate lots of models. Each black dot here is a model. So that's a lot of models. It's a lot of CPU time. But as I said, it has been shown that you can use these models, ab initio models, to solve molecular replacement problems. That's this example here. And there have been other people making use of other tools. Some folks in the UK have been doing this as well. So it's something you can try. But you're not going to be able to model a 300 amino acid protein this way, unless it conveniently happens to be in two domains that are small.
So typically, what's the IMS, the model, the starting model?
Well, I mean, I think if you talk to David and other people practicing this, that generally the models that you get on average are not very close to the right answer, of course. But you're going to have some things there are some models here that actually come out quite close. Yeah.
But most of them are far, far away.
Yeah, of course. I mean, it's very difficult to predict the structure of something without doing an experiment. I mean, that's, which is good, right? If you're a crystallographer.
And the real one I want is a successfully solved one.
These are things that's not relevant actually. That's something else. But you can take some of the models from down here, and yes, you can do molecular replacement to solve the structure. Yeah.
So you mentioned, of course, for something 300 amino acids, you're not going to be able to do a ab initio combination. But am I correct in thinking that if you believe you have a certain part of the structure that may be well modelable, you could model that part and use it to phase the
Depending on how much it is, but yeah, potentially, if that's what I was saying, if you had two domains that were sort of autonomous folding units in a sense, that could be modeled this way, yeah, you could approach the problem that way, or if you had some fraction that you believe could be modeled somehow, you could try and at least locate that. The problem is, unless you can get above about 50% of the structure actually placed by molecular replacement, it's still going to be difficult to go further. It's just in practice what tends to happen. Unless you've got things like noncrystallographic symmetry or other things that you can use to try and bootstrap and get better phases. So this is one approach. People have gone in somewhat other directions. So Isabel Uson in Spain, she developed this archan boldo method where essentially did a lot of this was a helical protein they were trying to solve here, helical bundle. They did lots of molecular replacement searches with relatively small alpha helices. Got lots and lots of possible solutions from phaser, most of which were probably wrong. But they took each one of those, then put them through some phase improvement, phase extension kind of approaches. And 3 of these 1,500 possible solutions actually fell out as giving a map and a model that made sense. So that's sort of getting to the idea of taking small fragments for molecular replacement. I mean, this is a well-defined unit of helix, and this is a helical protein. So maybe it's a good case, but since then they've worked on extending this to beta sheets. So there's some promise that this is a way to try and to be able to solve structures without having to know more than secondary structure elements. Still not going to be a routine thing, I don't think, but it's certainly not now. But development of that method could take it further. Okay, so the last topic is this idea that low sequence similarity models, we may be able to find a solution, but we don't actually know whether we've got an answer. And I'll talk about 2 approaches to this. So this is the fundamental idea. Let's say the true structure here is shown in yellow. The molecular replacement model that was placed was shown in purple. And they look pretty similar, right? We can recognize the same fold, but there's enough structural difference such that if you make maps, this is a different example on the right, but the same thing holds. If we make maps and the purple model is the truth here, and the blue is the model that we placed, there's enough difference in terms of coordinates of our input model that the phases are so poor that we get maps that are uninterpretable. The phases are just too far away from the right answer for us to give a map that we can interpret. And what's worse is that the phases we get are biased. You can see that they say a lot more about the input model than the truth. It's model bias. And I think people have probably encountered this several times, and in many cases probably given up and said, well, it wasn't a solution, and stopped. And what happened was Frank DeMaio from David Baker's group sent an email out to the CCP4 bulletin board and Phenix bulletin board asking people, have you got hard molecular replacement problems that you're not sure whether you've solved or not? And then he wanted to see if they could use Rosetta to try and pull those out in some way. And that turned into a collaboration with Tom and Randy and others to make something more formalized that would actually try and help solve this problem more generally. Yeah?
So in a case like this, are you going to have lower phase residuals for the lower resolution shells?
One would assume, I'm not sure if that was ever looked at, one would assume that yes, the phases essentially would match better at lower resolution or get worse and worse as you went to higher resolution. I would assume that, but I've never looked at that. I don't know if that was part of that work, but
How bad or how good are the phases and the error compared with the true
I'm going to guess those 60+%, maybe. I don't know.
These are pretty different. The one on the left, I just have a correlation coefficient.
Yeah.
So if you take the two maps at, I forget, about 2 inches resolution, you just do correlation, it's about 0.15.
Yeah. Yeah, so often the correlations are what, in the 20% sort of area. Phase error, I'm going to guess that's going to be a pretty high phase error to give you a map that's bad. Yeah. But essentially very difficult for a human being to try and interpret that thing on the right. If you can, we'd love to talk to you. Tell us something. So what Frank was interested in was, well, could we exploit the homology modeling aspects of of Rosetta and combine that with molecular replacement with phaser and everything else. So this is different from the ab initio model building. There's two components to what's done in Rosetta these days. One is trying to build models just given a sequence, which is a very good thing to try to do. But as part of that process, what they have to do is they go from a very simplified representation for a model, with, single balls for side chains, just a few atoms for a side chain. They have to go from that to a full atom model, then take that full atom model that they've created, which is fairly inaccurate, and then optimize it and make it more like a native protein. So that's what's been exploited here. That second part, trying to take an inaccurate all-atom model and make it look more like a native protein structure. The good thing there is that that's not limited to 120 amino acids. You can do with large structures, relatively large structures. And it takes a while to do computationally, but it's not super expensive. So the idea here is that we've got things that we do in crystallography and things that you can do in structural homology modeling, and they have some commonalities, but they also have some differences, and they're maybe complementary, and those two things together maybe would be powerful. Because essentially what we're doing typically in the crystallographic case for model buildings, trying to improve models, example is we use the density as a guide. Yeah, we trust the density, we're crystallographers. What the modeling people do is they trust chemistry and physics, because they don't have any data typically with what they're doing. So they're trying to make physically reasonable models just given atoms in space. What can I do to make them better? So those are two very different ways to think about the problem, but you can imagine combining them together could be quite powerful. So here's the sort of end result of all of that, is taking this where we started off with this yellow being our target where we would like to be, and purple being where we started. And as Tom said, the correlation coefficient for that purple model is very low. It's a map that essentially would be uninterpretable to the human eye. And if what you do is you take that purple model and give that and the current electron density map, which is very, very poor, you give that to Rosetta and say, well, give me models that you've tried to make better that are also consistent with that density map. And one of the fundamental ideas here is that there is something useful in that map. It's not totally random. It has something useful in there. We just can't see it and figure it out for ourselves. And you get it to make a few models, because there's some stochastic random component to this. And this is a typical model that it comes out with the blue one. And you can see it looks a little bit closer to the yellow one. And you can also see the map correlation has improved. It's nearly 30% from about 17%. So that's an average one. If you take the best one as judged by the free R factor, you get the green model, which is a lot actually closer to the truth and has a correlation coefficient of about 0.34. So just one cycle of this, we managed to get a model that is significantly closer to the truth. And you can imagine taking that model and going back and repeating this again. And you can imagine combining that with automated model building potentially as well, or density modification, other things to try and improve density. Now you could say, well, okay, so Rosetta is just some fancy way to move the atoms around. Why wouldn't you just be able to do something like simulated annealing, which is a powerful way to move things and optimize models? A big fan of that. But so this is just to compare the difference between those two approaches, though. So in blue, we're looking at the correlation of a model after doing something to it. So the higher the better against the frequency. And you can see that if we do simulated annealing, we start off around about 2.9 here. We get a few models that are a little bit better. So there is some models where there's a bit of an improvement, but on average, the Rosetta models are always shifted to the better all the time. I mean, there are some that aren't. It made a really crappy model here for some reason, got a lot worse. But generally, that's not the case. And that's because if we just compare the models that you get out from annealing versus Rosetta is able to search more of conformational space, is the bottom line. It can make jumps that, because it repacks things, that even simulated annealing isn't able to do. So this is the procedure. Do molecular replacement, do your best to improve the phases, apply the Rosetta procedure that I mentioned, take the best models, then apply the Rosetta procedure again, try and do auto-building to improve things, and just go through this several times.
This does imply that you've found an approximate molecular replacement.
Yeah, you have to have found a solution. Now, of course, if your solution is incorrect, this will not work. So this is a good way to test whether you've got an answer. It's a somewhat expensive test in some ways. It takes, but it's a computer time. It's not your time, so it's fine. And there is an option here, of course, to take your search model and put that through Rosetta to begin with to try and improve that model before you even go into molecular replacement. That was a question that came up this morning. So then this just goes through the example of the MR solution is shown in blue. What we're trying to get is what's shown in yellow. This density map is not so bad, but it's still difficult to interpret. But it shows you after going through one round on the right, you get the purple model that's closer to the yellow. It's improved. And going through several rounds of that, you end up with a density map that can actually be rebuilt by auto-build automatically to give you the green model. So we can essentially just rebuild the structure given the phases that we have. So this is a way to kind of bootstrap out of this poor solution into a space where we've got something that makes sense. And this just shows you that you can apply this over a range of resolutions. Some are going to be better than others. Of course, lower resolution, you have less information. It's not going to work as well potentially, but it shows you just generally you get improvements across all resolution ranges. The better the resolution, the more this will improve things, of course. It's just a general thing. So that's one approach. And in the last 5 minutes, I'll describe a different approach, which Tom developed, which was, let's go back to our NMR example here, where yellow is the true answer and purple is the molecular replacement model that we placed. And if you look at it, what you might notice is that a lot of the differences are not because things have changed secondary structure or conformation. It's just because they've moved in space a little bit. A prime example would be this helix. If I knew I shifted this helix by half a turn in that direction, I'd have it in the right place, right? So these changes are just local shifts. And often they are just translations of parts of the structure. So maybe we could exploit that. Again, the fundamental idea being that there is something in these very noisy maps that is real. If there was no information in these noisy maps, we would be stuck. We wouldn't be able to do anything. But we assume that there is something useful there. And the idea here is that you just visit each C alpha position in your current model, create ideal density in a sphere around that region, for the 5 residues around you, calculate the ideal density, and then see, is there any way I can move this ideal density with respect to my current electron density map, this very poorly phased one? Can I move that density such that it improves the fit? So this is a way to try and use a large number of atoms simultaneously to try and find shifts in real space to move the model. And you do it for each residue at a time, and you'll get shift vectors for each residue. You have to smooth them to stop residues going in wildly different directions, but you can do that. And that's just what's shown here. Like taking this one particular residue here, this is the ideal density shown in purple. And this just shows that if we shift that purple density by the direction of this arrow here, that actually gives us a better fit to the blue density based on correlation. So you can do that, and you would get this shifted model out at the end. We started with the light blue model. At the end of doing this, we get the yellow model. Now, of course, it's probably going to cause geometric distortions in the model because we've shifted residues kind of on a somewhat individual basis. So then you have to do some reciprocal space refinement, again, to make the model more consistent with chemistry, and that's what's shown in orange here after doing that. And you can see that some parts of the model have shifted quite a bit, some less. But this now gives me a model that I can now calculate a new set of phases from and make a new map. And that's what's shown in purple here. It might not look much better, but that is a better map. You can calculate the correlation coefficient of that map to the true answer and see that it is a better map. So you can then use that map as the input and do it again. And you can do it several times. And, yeah, I know. And at the end of the day, you get a map, this red kind of map that is good enough to be automatically built using the automatic building methods in AutoBuild. And the change from the blue model, you can see is we ended up with the yellow model in terms of a refined model after the morphing, and in green is what was rebuilt into that map by AutoBuild. So you can see we've had very substantial shifts in atoms here, in secondary structure elements. So this process is called morphing, and is a bit computationally more efficient than the MR Rosetta approach. There are some things that MR Rosetta can solve that morphing can't. So there's a few cases, in terms of test cases, where you really need something like MR Rosetta, but a lot of the things you can do with morphing. And then I should also point out as well that just doing enough refinement can make a big difference. So this is taking some of those examples I showed you for MR Rosetta and just throwing 100 rounds of reciprocal space refinement at it with Phenix Refine. And just looking at the free R factor, you can see some of these things don't get any better, but there are some structures where the free R factors decrease significantly. So it's just a matter of running enough cycles to actually have the model move enough to actually make a change. So that is another viable option in many cases, just do a lot of refinement. Again, it may seem like, 100 cycles, but you're not doing the work, the computer's doing the work. So hopefully that's not a cost to you, really. I don't know how they charge you for things here. So just to summarize, hopefully I've shown you some new algorithms that increase the success rate in molecular replacement, one way or another. This is what I would suggest that one do if you're trying to solve a molecular replacement problem. Clearly, applying the standard methods, that includes things like anisotropy, correction, and accounting for translational NCS. You should look at the indicators of success, like the translation function z-scores, packing, things like that. As a side note, it's always good to take your cell dimensions and symmetry and check it against the PDB. There's a little tool in Phenix that does that. Just give it your MTZ file or type in the unit cell dimensions, and it'll come back and tell you if there's anything in the PDB that looks like it's got a similar cell dimensions. We've solved MVP in my group before, just by accident because it was in there. We managed to crystallize it. It likes to crystallize more than the protein you're working on, that's my guess. So this is always a good thing to do. I've seen
carbonic anhydrous.
Yeah, exactly. So there's a whole set of proteins from E. coli, for example, that are not that hard to crystallize, and could be of a similar size to the thing you're interested in. So it's always a good check to make. So if you do microplacement and you think you've got a solution but you're not sure, the first thing I would try is just throw it into a lot of refinement. Do 100 cycles of Phenix Refine, or your favorite program, whatever that is, and see what happens. Maybe the free R factors come down and you're pretty clear you're okay. If that doesn't work, I would try morphing because it's fairly fast, and you can try them in parallel if you want. And that may well pull things out and give you the answer. If that doesn't work, try MR Rosetta. That will take longer, and you have to install Rosetta, and there's a little bit of an overhead in terms of setting that up, but it's nothing terrible. And if you're desperate, of course, trying Rosetta or similar tools for ab initio model building is it's a route to take. But you should be realistic about success. I also think, look at the archan boldo or Borges approach that Isabelle Usson has developed as well. And then final advice is if you have experimental information, include it. So I mentioned MR SAD, as Tom did. The combination of molecular replacement and some phasing from, say, SAD phasing is very powerful. So if you've got those two things together on a hard problem, you might be able to crack it in cases where you can't. Okay, so I'll finish and just say thank you to a lot of people involved in this. Randy's group for the developments in Phaser, the collaboration with Frank and David and a lot of people who provided data, difficult cases for the MR Rosetta, and Tom, especially for his developments for morphing and things like that. Okay, thank you. Well,
so, right after molecular dynamics was introduced, there were a spate of incorrect structures until the free R factor was developed. I'm just wondering, given you have more powerful tools to move atoms around to better fit the data, is there a free R immediately being applied to the MR Rosetta or the morphing?
So the free, because those both include reciprocal space refinement, free R's are calculated along the way, yes.
So are there ever any cases where the wrong solution gets kind of bent up to give you a good looking map? Say the free R tells you that you went the wrong direction?
Not that I'm aware of, no. It's difficult to imagine how that would happen. Maybe in some pathological case, but a priori there's no reason to believe that would happen. Because the model still has to fit the diffraction data in some way. And we tend to assume, rightly or wrongly I guess, that there is a unique answer for a given set of amplitudes.
Well, Rubisco was built backwards, right, and refined successfully. So
But the free R was...
Right, before the free R.
Yeah.
I'm just saying, you have examples where you apply the procedure and you calculate the free R and it's gone way up and it's kind of a whoops.
No,
But you pushed into a local minimum.
No.
I haven't seen that.
no.
The model we look at, I mean, it's really good in real space. So despite the fact that the high resolution phases are not good, if you just take low resolution phases, they should be very good. And so if you just take them and then use phase extension, and forget about the model, maybe you can get a good result from this.
I mean, so if there are better methods to do that, historically, Tom could say more, but the experience is you can't really extend from very low resolution phases to high resolution. That is not successful, generally.
Okay.
Otherwise, that's what we'd do.
Especially the low resolution
Conceptually,
phases are very good.
Well, I don't know how good they are. I suspect they're still quite poor, but they're certainly better than the high resolution one, that's for sure. Yeah. So conceptually, yeah, if we could do that, that's what we'd want to do. Of course, we'd want to take some very reasonably okay low resolution phases
Right.
and project to high resolution.
Right.
But that's not been technically possible. I mean, what your experience is, but that is not something that can really do.
Yeah, so if we could do that, it would be really great. So actually, today, people regularly extend from low to high resolution if there's significant amount of non-crystalline.
Yes, you can do it with NCS.
That's done routinely. That's very powerful. But so far, we are not successful. Extending from low to high resolution with just moderate solvent.
Yeah, in the general case.
You can go from medium to medium high or medium
Yeah,
high.
you can go a little
To
way.
shell, right?
Yeah, but that's about it. Yeah. So there was a question here.
I was just wondering, when you deposit structures using solving using molecular replacement, are you supposed to put in all of these statistics, correlation coefficients, and do you submit that to the I've
so-
never seen it in a publication.
No, it's a very good question, actually. So you're not asked to do that. Having said that, though, I certainly worked with the PDB a long time ago to develop the appropriate tags for information, so that one could deposit things like the model you use for molecular replacement, statistics about the molecular replacement process. Same thing for phasing. So there is actually a wealth of possibility for depositing all of that. So there will be a push, bless you, certainly in the context of Phenix over the next few years, to make that automatic, so that when you solve your structure, you can press the deposit button and we will suck that all up and put that into the protein data bank. Now, people like the JCSG, because the largest structural genomics centers were asked to do this, have been doing this for some time in sort of one form or another. So they've been very good about providing more information, but the general users have not been asked to do that. But it is valuable information, and we think that it should be in there. But if the PDB asked you to do it all by hand, you would revolt, I'm pretty sure, and there would be a riot. So it has to be more automatic. It has to be done by the software, I think.
For presumption is that those are intermediate results, not necessarily germane to the final quality of the coordinates, right? That's the presumption.
That has been a presumption, but of course knowing about how you got to that point can be very informative. And if anybody else wants to reproduce your work at the end of the day, they need to know that. And it's very useful for developers and everybody else as well. It's a wealth of information.
All right, well, let's take a short break. And, sorry, it's finding us a break to get this right. But we need to stop here for a minute and take a break. The bathrooms are farther down the hall.